Hey everyone, how about we look at L'Hopital's rule? Day 2. This is 42. This is, in fact, assignment 42. Our second to last before we start the AP exam review. Cool. So, let's have some review first. Can we do this problem? Evaluate this limit as x heads to 0, 3x minus sine x all over x. Pause the video, give that a try. Any method you like. Okay. So when I plug my zeros in, I do get 0 minus 0 over 0. And so I know that's my indeterminate form. I know that I could split this up from our work in chapter 2. X approaches 0, 3x over x minus the limit as x approaches 0, sine x over x. This is going to give me the limit as x approaches 0 of 3 minus the limit as x approaches 0 of sine x over x. 3 minus 1 is 2. So that's the chapter 2 approach. And tell me about the L'Hopital's rule approach. Well, since I think I want to start. If f equals 3x minus sine x and g equals x, f of 0 equals g of 0 equals 0, and f prime and g prime exist at x equals 0, use L'Hopital's. I mean, it's really having to state this preamble really sort of means I think I'd prefer to do this and save L'Hopital's rule really only for those situations where I can't do this. All right, so we've got that, and because of this, we know that we can use L'Hopital's. So that would be the limit as x heads to 0. The derivative of this is 3. The derivative of sine is cosine, and the derivative of x is 1. So I plug my 0 in there. 3 minus cosine 0 equals 3 minus 1, or 2. I mean, we should get to the same place, but sometimes we can or cannot find ourselves able to algebraically manipulate the situation. Okay? How about this one? The limit as x heads to 0 of square root of 1 plus x minus 1 over x. Give that one a try. Yeah, I think this is a great example of yeah, I think I'm going to use L'Hopital's rule. So what does that look like? Well, if f equals square root of 1 plus x minus 1, and g equals x, f of 0 equals g of 0 equals 0. And don't just say it, you should confirm it. If you plug a 0 in here, you have square root of 1, which is 1, 1 minus 1 is 0, over 0, great. And g prime of 0 and f prime of 0 exist. I was a little wondering if this would exist, but remember, this we've shifted the graph left 1 and down 1. And so we're looking at something like that. And we definitely see that that function has a derivative at that point. So use L'Hopital's. Okay, so that means we have the limit as x heads to 0. Derivative here, 1/2, x plus 1, minus 1/2, derivative here is 0, over 1, because the derivative of x is 1. Now when I plug my 0 in, I get 1 over 2 root 1, or 1/2. We can certainly confirm that. We can certainly confirm that by using a table. Okay? How about this last one? What do we do in this situation? The limit as x heads to infinity of x to the third minus 2x squared plus 1 over 4x to the third plus 2. Now we know from pre-cal that when the degrees are the same, we just look at the ratio of leading coefficients. So we know we should come up with 1/4. And we talked about this method back in chapter 2, where we would multiply top and bottom by 1 over x to the highest degree. And that would give us the limit as x heads to infinity of 1 minus 2 over x plus 1 over x to the third over 4, right, because that might cancel, plus 2 over x to the third. Now when I plug these infinities in for x's, I get 2 over infinity. Well, that's no pizza for you. And 2 over infinity cubed, definitely no pizza for you. And so all we're left with is 1 minus 0 plus 0 over 4 plus 0. And so we can get 1/4 that way. Okay, but now what about L'Hopital's rule? First, is it appropriate here? All right, well, I definitely see that if I plug in infinity here, I'm going to have infinity over infinity. So I'm going to say if f equals x to the third minus 2x squared plus 1, and g equals 4x to the third plus 2, and f of 0, oops, whoa. Yeah, I'm kind of sad face about that, because I think I'm going to say g of infinity equals infinity. That's not quite that line we were talking about, huh? But we know that infinity over infinity is okay. And there are actually algebraic ways, maybe we can look at them today, that could create infinity over infinity for us from a 0 over 0 situation. But I don't think I'm going to go there. Instead, I think I'm going to say use L'Hopital's. Okay, so my derivative here would be the limit as x heads to infinity, 3x squared minus 4x over 12x squared. Okay. Still, when I put infinities in, I get infinity over infinity. I probably want to say something like use L'Hopital's again. And so now we're going to have the limit of 6x minus 4 over 24x. And this is as x heads to infinity. Again, I get infinity over infinity, so let's use L'Hopital's. Okay, and that's going to give me the limit as x heads to infinity of 6 over 24, which is 1/4. Gosh, that's a lot of work to use L'Hopital's rule. Yeah, so I might use something else, like something we learned in chapter 2. If the problem says you use L'Hopital's, you must use L'Hopital's. But if it doesn't, then you have flexibility in what you're going to do. Okay, so yesterday we said that if we have 0 over 0 or infinity over infinity, then we can use L'Hopital's directly, provided we put that preamble down. But there are other indeterminate forms, like 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, and infinity to the 0. All of these can be rewritten into that form, but I can't use L'Hopital's directly in these situations. I'm gonna have to do some rewriting in these cases. So let's look at those, and I know that many of you are very keen to know how that isn't always 1. Don't worry, I'll show you. Okay, so let's start with 0 times infinity, in that case. So when you have this form, f times g, you must first rewrite this into the form f of x over, not g of x, but 1 over g of x. So what I'm doing here is I'm taking one of these functions, flipping it upside down so it can be in the denominator, right? Because if I'm looking at this, then I can say, oh, look, I could do flip and multiply. So if I flip and multiply, I'm going to end up here. So this is sort of doing the reverse flip and multiply. Okay, so I have to choose one of my functions to go into, to go upside down into the denominator, to have the reciprocal in the denominator. How do I know which function? Well, I'd say whichever one looks easier to work with, because we could also say, well, or g of x over 1 over f of x. Doesn't matter which one goes in the bottom, it doesn't matter which one you call f, which one you call g, just move. Okay, so the limit as x heads to infinity of x times sine of 1 over x. Okay, so this is our situation, and if I plug in infinity here, 1 over infinity is 0, sine of 0 is 0, and 0 times infinity, yeah, I've got that situation. And we've got two choices here. Either we could write this as sine of 1 over x over 1 over x, right, because we're flipping x over 1 and throwing it in the denominator. Or we can have x over 1 over sine of 1 over x. Frankly, this looks a lot harder to try and take the derivative of than that. So, yeah, no, I don't want to do that one. And I'm going to just rewrite in this manner. So it's to infinity. Okay, so now when I plug in infinity here, 1 over infinity is 0, sine of 0 is 0, and 1 over infinity is 0. And so I have 0 over 0. Okay, and since I have 0 over 0, that tells me that if f is sine of 1 over x and g is 1 over x, and f of 0 equals g of 0 equals 0, and f prime, that's that infinity case, hold on. If I plug in infinity, I get infinity. And I do get 0 over 0. That is equal to 0. And f prime and g prime exist x not equal to 0, well, I got around that, then you use L'Hopital's. Okay, so what will it look like if we have L'Hopital's here? So take the derivative of the top. The derivative of sine is cosine. Leave the inside alone, times the derivative of the inside over the derivative of the denominator. Oh, isn't that interesting? Those cancel. So now I have 1 over infinity, which is 0, and the cosine of 0 is 1. And there's the value of my limit. Done, done, done. So when you have 0 times infinity, flip one function reciprocal into the denominator to create 0 over 0 or infinity over infinity. Okay, so how about you do this one? The limit as x heads to 0 from the positive of x ln of x. Okay, that's sort of important because we know ln doesn't exist at 0, nor does ln exist from the negative side of 0. So this is the only way we really can approach this function. Okay, just in case you came back saying, but Mr. Cooper, this is 0 times 0. Yeah, it's not 0 times 0. 0 times 0 would be 0. This, however, when I think about this graph, and the reason I really wanted you to be comfortable graphers so you could think graphically. As x heads towards 0 from the positive side, look where my function is going. That's negative infinity times 0. Okay, so I really do have this situation, and I really can flip one of them. So the limit as x heads to 0 from the positive of ln of x over 1 over x. I mean, you could certainly do this other thing, where you said, hey, let's do the limit as x heads to 0 from the positive of x over 1 over ln of x. And that just looks heinous. So I don't want to do that. Instead, this is the one I want to do. Now, if I plug in my zeros from the positive. Okay, so that's infinity. 1 over 0, infinity. I get infinity over infinity, and I'm good to go. So, statement, because this thing isn't differentiable at 0, but that's okay. We only want that. Yeah, this is a little harder for me to feel like I can justify, because I know that f of 0 if f equals ln of x and g equals 1 over x, f of 0 from the positive side equals g of 0 from the positive side equals what? What do we get? No, these are infinity sort of things, right? That's a minus infinity on that one. And this one is a positive infinity. I'm just not feeling the love here. This sort of bulletproof AP exam thing that they want me to write is really kind of troubling here. So let's imagine that I picked a better example. Oh, no, I still want to do this one. Don't get me wrong. I just don't know necessarily how comfortable I am with trying to write that prelude that says use L'Hopital's. So I'm going to walk away from that and say, okay, I use L'Hopital's. And now I've got the limit as x heads to 0 from the positive of, we had ln on top, and we have 1 over x on the bottom. Okay, and now if I plug 0 in again, I get infinity over infinity again. This feels a little like I don't want to do that. Well, don't. That's why we taught you the other methods first. You know, I can simplify this algebraically to be 1 over x times negative x squared over 1, which is going to be the same as x heads to 0 from the positive of negative x. So if I plug a 0 in there, I get 0. Okay? Yeah. I think that I do want to say that this stuff about these limits, especially limits involving infinity, yeah, gonna be kind of important in Calc 2 when we're talking about convergence and p-tests. Okay, so how about this next form? Okay, we've done the 0 times infinity situation. Well, we've got some more to look at. This one's a favorite. Infinity minus infinity. Is it infinity? Is it 0? Is it 7? I don't know. It's situationally dependent. So what I know is that somehow I have to rewrite this so it's in 0 over 0 or infinity over infinity. Remember, no L'Hopital's until you're here. Okay, so this isn't, no, I can't use L'Hopital's first. I have to rewrite this in some manner to get one of these cases before I can use L'Hopital's rule. So how about this one? The limit as x approaches pi over 2 from the negative side of secant x minus tangent x. Well, we know that there are vertical asymptotes on these graphs at pi over 2. So yeah, that's going to be that infinity minus infinity thing, and I'm going to be sad until I think, well, let's rewrite this so that we can have one of these situations. And I remember when we were talking about using our trig identities, you know, we could rewrite these as 1 over cosine x minus sine x over cosine x. And so now I'm looking at the limit as x heads to pi over 2 of 1 minus sine x over cosine x. Now when I plug that pi over 2 in, sine of pi over 2 is 1, 1 minus 1 is 0, cosine of pi over 2 is 0, and so now I've got 0 over 0. If f is 1 minus sine x and g is cosine x, and f of f of pi over 2 equals g of pi over 2 equals 0, and f prime and g prime exist, then use L'Hopital's. Okay, so let's use some L'Hopital's here. I use L'Hopital's. I take the derivative of the top, and I get the derivative of negative sine is negative cosine. I take the derivative of the bottom at negative sine. Now when I do my direct substitution, I have minus cosine of pi over 2 minus sine pi over 2, which is 0 over negative 1, or 0. Okay, so that's the value of that limit. So when I have the situation infinity minus infinity, or 0, infinity minus infinity, I want to rewrite this so that I can get into 0 over 0 or infinity over infinity. So what can you do with this one? The limit as x approaches 1 of 1 over ln of x minus 1 over x minus 1. Why don't you give that one a try? Come back when you're done. Hi everyone, welcome back. So the thing about 0 over 0 or infinity over infinity, That's one object, one term. With infinity minus infinity, and yes, this is, because ln of 1 is 0, 1 over 0, I'm going with infinity. 1 minus 1 is 0, 1 over 0 is infinity, and so I have infinity minus infinity. But what I notice here is each of these is one thing, right? There's no two things joined with addition or subtraction when I'm looking at 0 over 0 or infinity over infinity. And so a strategy that often works is make a common denominator. So now I'm going to have the limit as x heads to 1 of x minus 1 minus ln of x over x minus 1 ln of x. Okay, so what happens here? 1 minus 1, 0, minus ln of 1. ln of 1 is 0. So we have 0 minus 0 or 0 on top. 1 minus 1, 0. ln of 1, 0. 0 times 0 is 0. 0 on the bottom. And 0 over 0. So if f is x minus 1 minus ln of x, and g is x minus 1 times ln of x, and f of 0, is it 0? No, 1, equals g of 1 equals 0. Then, and f prime and g prime. In fact, I just want to know out 1. And it's true that both of those out 1 exist. Then use L'Hopital's. Okay, so what's this going to look like when I use L'Hopital's? I'm taking the derivative here. I'm going to have the limit as x heads to 1 of 1 minus 1 over x. And here, that's right, I have to use the product rule. So the derivative of this is 1 times ln of x plus the derivative of that times x minus 1. Okay? I think I want to tidy this up a little bit. I'm going to distribute here. And that's going to give me the limit as x heads to 1 of 1 minus 1 over x. And on the bottom, 1 of x plus x over x is 1 minus 1 over x. Okay, now, do I still have, or do I now have a 0 over 0 or infinity over infinity case? So if I plug my 1 in here, 1 over 1 is 1, 1 minus 1 is 0, ln of 1 is 0, 1 over 1 is 1, 1 minus 1 is 0, so I have 0 plus 0, that's 0, and on top, I have 1 minus 1, which is 0, and so I have 0 over 0. So this looks like a situation now where instead of having two separate things, I've got that one thing. I have used L'Hopital's rule. So I think I'm going to do it again. And since I've already sort of explained that I know the precondition, I think I can get away with that. And so I have a limit as x approaches 1 of 1 over x squared over 1 over x minus plus 1 over x squared. Okay, I think at this point, when I plug in 1, though, look what happens. 1 over 1 is 1, 1 over 1 plus 1 over 1 squared. And so we get 1 over 2. And there's the value of my limit. Okay? Good. Nice. So, I think in general, when I see this, I could say, usually, make a common denominator first. Okay. And for 0 times infinity, this is where we're going to put the reciprocal of one of the functions in the denominator. Okay, now let's move on to our last type. 1 to the infinity, infinity to the 0, 0 to the 0. So in all of these situations, I'm looking at a situation where I have a function raised to the power of a function, okay? And we know that if y equals this, from our logarithmic differentiation, what would we do? That's right, we would take the ln of both sides. We'd bring down that power. Remember, it's not ln times f of x, it's ln has eaten f of x. And so this is what we're going to work with first. We're going to do that take the ln of both sides first and see where that takes us. Okay? Okay. So with that in mind, how about this one? The limit as x heads to 0 of x to the x power. Okay, well, yeah, that's going to be 0 to the 0. Sure. So I get 0 to the 0, and I think that's not so good. So what if I say that y is equal to x to the x? And then I take the ln of both sides and bring this down. Well, I get the ln of y equals x, ln of x. Fabulous. So what's the limit as x heads to 0 of x, ln of x? Well, funny you should mention it, because as we approach 0 from the positive side, this thing is headed to negative infinity. And if we plug the 0 in there, oh, that's a 0 times infinity. Wait a minute. So this now is that case that we looked at first. This is 0 times infinity. And what did we do in that situation? Well, we rewrote it some more. We flipped one of these into the denominator as its reciprocal. And so now when I plug in zeros, I get infinity over infinity. And I say, great, let's say if ln of x is f and 1 over x is g, and f of, oh god, I just don't like this because that really needs to say from the positive. Okay, we'll fix it that way. That feels better. 0 from the positive equals g of 0 from the positive, but they're both equal to infinity. That's going to be the infinity over infinity situation. And f and g are differentiable for x not equal to 0. Good. Looking from the positive side. Then use L'Hopital's. Okay, so I'm using L'Hopital's rule. What's that going to look like? That's going to look like a limit as x heads to 0 from the positive side of 1 over x over negative 1 over x squared. Putting in zeros, I still get infinity over infinity. But this is where I think, hey, what if I do that? Flip and multiply. And so now I'm going to have the limit as x heads to 0 from the positive of negative x. Oops. Negative x, right? Because that cancels that. Okay, and now I plug in my 0, and I get 0. But wait. This is what ln of y was equal to. Remember? ln of y is this. So I need to exponentiate both sides. Whoa! And I just made a linkage error. Because this is now 1, and this is not 1. So watch out. Instead, yeah, let's make a new line. to say that if 0 equals ln of y, and we exponentiate, we're now going to have 1 equals y. And remember that y was the limit as x heads to 0 from a positive of x to the x. And so we're going to say that this function, coming from the positive side, is approaching a value of 1. Okay, so, wow, wasn't that interesting? When I had 0 to the 0, I had to take the log of both sides to get that down. And then I was actually looking at this. And so I had to use the technique for this one where we flip one of the functions into the denominator. Great. What's next? Here we go. How about the limit as x heads to infinity of x to the 1 over x? Ew. Do we have to, Mr. Goodler? Sure, because this is going to be the infinity to the 0 case. And again, I'm going to say that y equals x to the 1 over x. And I'm going to take the ln of both sides and bring this down. And so now I have ln of y equals 1 over x ln of x. Okay, so yeah, and you might even want to think about that then as the limit as x heads to infinity of ln of x over x. Well, when I plug in an infinity here, I know that's headed up forever, right? And what's happening here? Yep, also infinity. So that's good. And that makes me feel like I can say the limit, and if f is ln of x and g is x, and f of infinity equals g of infinity equals infinity. I feel really uncomfortable writing that. And f prime and g prime exist, then use L'Hopital's. Okay, so L'Hopital's. I'm here, and I want to use L'Hopital's. That's going to give me the limit as x heads to infinity of 1 over x over 1. I get 1 over infinity, which is 0, but don't forget, that's what the ln of y is. ln of y equals 0. We exponentiate, we get y equals 1. Okay. Nice. All right. So we've now had 0 to the 0, infinity to the 0. Drum roll, please. Here it comes. The limit as x heads to infinity of 1 plus 1 over x to the x. And you may not recognize this at first, but you may. You may indeed. Okay, so I plug in infinity. 1 over infinity is 0. 0 plus 1 is 1. And I have 1 to the infinity. And when I have 1 to the infinity, I think, whoa, I got to take that ln on both sides, because look, I have function raised to a function. So I'm going to say y equals 1 plus 1 over x to the x, and therefore the ln of y is going to be x ln of 1 plus 1 over x. Good. Now, what happens if I think about the limit? X 1 plus 1 over x. So that's going to be the ln of 1, which is 0, times infinity. Oh, well, I remember 0 times infinity. This is the case where I have to flip one of these upside down into the denominator. I'm going to flip that one, because, no. So now I'm looking at the limit, as x heads to infinity, of ln 1 plus 1 over x over 1 over x. Great. I plug my infinities in, and I get 0 over 0. So let's write a little justification. If f is ln 1 plus 1 over x, and g is 1 over x, and f of infinity equals g of infinity equals 0, then, and, God, there's so many preconditions, f prime and g prime exist for x not equal to 0, then use L'Hopital's. Okay, so what's using L'Hopital's going to look like? This. Okay, so I'm going to have the limit as x heads to infinity of 1 over stuff times the derivative of stuff. And the derivative of this is 0, and the derivative of 1 over x is negative 1 over x squared. All over the derivative of this is negative 1 over x squared. Look, those cancel. Now when I plug in my infinity, I get 1 over infinity, which is 0. I get 0 plus 1, which is 1. I get 1 over 1. So I know the ln of y is 1. But I need to know what y is. Y equals e. And so guess what? This thing, this 1 to the infinity thing, that's in fact our definition of e. This is in fact where e comes from. No, really, Euler said, let's let the number of compoundings head to infinity. And when the number of compoundings head to infinity, you get the number that we call e for Leonard Euler. Yay. All right. Well, there you go. See, that was a situation where you had 1 to the infinity, and in that situation, 1 to the infinity was e, not 1. See, told you. And look, it was even using something you've known about for a couple of years. All right, so how about you do a little practice with this? Yeah, how about you do a little practice with this one? The limit as x heads to 0 from the positive of x sine x. Okay, give it a try. See what you come up with. All right. So I have 0 to the 0 situation. That means I want to do, say, this x to the sine x. So ln of y equals sine x over x. Nice. And so now I'm looking at x heads to 0 from the positive. That's sine x times x. I plug my zeros in now. I get a negative infinity times 0. I know that's that other situation where I have to take one of these and flip it into the denominator. Well, which one? It's a good question. I think actually I'm going to do this. Sine x over x. And, if I think about it, I'll go back and try the other one. Ln of 0, that's 1 over infinity. That's 0 pizzas for you. Sine of 0 was 0, and so you have 0 over 0. So if f is sine x and g is 1 over ln of x, or ln of x to the negative 1 power, and f of 0 from the positive equals g, 0 from the positive equals, they were equal to 0. And f and g prime exist for x not equal to 0, and use L'Hopital's. Okay, so I use L'Hopital's. I take the derivative of the top, that's easy peasy, I'm going to have the limit as x heads to 0 from the positive of cosine x. Be careful with this. Remember that this is the same as ln of x to the negative 1. So when I take the derivative there, that negative 1 comes down. I have ln of x to the minus 2 times, what's the derivative of ln of x? That's 1 over x. Okay, so what am I looking at now? Well, it appears as though I'm looking at, and I think maybe sometimes just rewriting it in a more tiny form. The limit as x heads to 0 from the positive of cosine x over negative 1 over x ln of x squared. If I plug my 0 in here, cosine of 0 is 1. If I plug my 0 in here, from the positive, that's going to be negative infinity. That's going to be 0. So I really don't want to deal with that. I'm not ready for direct substitution. How about if we do this? How about if we do that flip and multiply? What happens then? Negative cosine x times x ln of x squared over 1. Does that help? I plug in 0. No, I have infinity. I have 0. No, that's definitely not a happy time. Yeah, that's I don't feel like I'm quite getting there. Maybe I missed something here. I will say that there's this situation that occurs when people are doing L'Hopital's rule problem, that they just keep taking L'Hopital's, using L'Hopital's rule, even though it's not a L'Hopital's rule situation. So if I plug in my 0, that's going to be a 1. If I plug in my 0, yeah, that's what's bothering me. If I plug in my 0, that's infinity. Oh, 1 over 0 is infinity. Infinity times infinity. 1 over infinity. Yeah, see, this is that case. This is that case of taking it too far. This works. I think it works. No, I didn't. Because this was going to be infinity. But look, it's 1 over infinity. Boy, this really... So, you know, I seem to recall that this was us trying to do this by flipping the ln into the bottom. And look, it got us to this place that wasn't happy. Hey, so what if instead, when we're looking at sine x times ln of x, that we think actually about flipping this one? Okay, so that's going to be the limit as x heads to the 0 from the positive of ln of x over 1 over sine x. And yes, this is equal to cosecant x, but I almost never want to deal with that. Okay, so what do we have here? Sine of 0 is 0, 1 over 0. We have infinity over infinity. So if f is ln of x and g is 1 over sine x, and f of 0 from the positive equals g of 0 from the positive equals infinity. Okay, use L'Hopital's. No, I didn't say that part about differentiable. And f prime and g prime exist for x not equal to 0. That's a little trickier with this one because this one has a bunch of vertical asymptotes, but I'm going to go with it. I'll use L'Hopital's. Okay, so what does L'Hopital's rule look like here? Okay, I've got the limit as x heads to 0 from the positive, 1 over x. And here, you know, I'm tempted to rewrite this as cosecant, but I actually think I'm going to do quotient rule. Low d high minus high d low over low squared. Okay, so if I plug in a 0 here, I get 1. 0 minus 1 is negative 1. And here, sine of 0, that's 0. So I have negative 1 over 0, that's infinity. And I have 1 over 0, that's infinity. So I feel like I've got infinity over infinity. Let's maybe rewrite this using our algebra skills. What will that be? That'll be the limit as x heads to 0 from the positive of sine squared x over negative x cosine x. I believe. Yes? Yes. Okay. If I plug in my zeros, I get 0 on the bottom, I get 0 on the top. I'm definitely ready to say if f equals sine squared x and g equals negative x cosine x, and f of 0 equals g of 0 equals 0, and f prime and g prime exist, then use L'Hopital's. So what do we get when we use L'Hopital's here? Okay, use L'Hopital's, I get the limit as x heads to 0 from the positive of 2 sine x cosine x over, product rule, negative 1 times cosine x plus negative x, negative cosine is sine. So I'm just going to say x sine x. Okay, so what happens when we plug our 0 in now? That's going to be a 0 on the top. That's going to be a negative 1. And the sine of 0 times is 0. And I said a 0 on the top. And that looks like 0 over negative 1, which is 0. Fabulous. Now, don't forget that this is ln of y. And so y equals 1. Ah, that was an exciting long problem. And yes, I would actually put that on a test. No, really I would. Okay, how about this one? The limit as x heads to 0 from the positive e to the 3x over x squared. Will you evaluate that, please? So, ideally, you came to the understanding that this was 1 over 0 squared. And that, I'm going with infinity. Yeah, this is not a L'Hopital's rule situation. This is just, I know that 1 over 0 is either infinity or negative infinity. This is always positive, and this will always be positive. So positive over positive gives me positive. Okay? Not L'Hopital's. Not everything is L'Hopital's. I'm sorry. Not everything. So, how about 1 or 2 more? How about the limit as x heads to infinity of x ln x over x plus ln x. So what do you notice here? Well, infinity times 0. Now that's heading towards infinity. Infinity times infinity. I've got infinity on top, and I've got infinity plus infinity on the bottom. So I'm looking at infinity over infinity. So why didn't I say if f equals x ln of x and g equals x plus ln of x, and f of infinity equals g of infinity equals infinity, and f prime and g prime exist for x not equal to 0, then use L'Hopital's. Okay, so I'm going to use L'Hopital's rule here. Take the derivative of the top, and it's a product rule. So ln of x plus x times 1 over x. And on the bottom, no product rule, just 1 plus 1 over x. Okay, these are going to cancel. And now when I plug in infinity, I get infinity on the top, 1 over infinity. And that's 0. 0 plus 1 is 1. So I've got infinity over 1, which is infinity. Yeah, I get infinity here. Did I drop us in it? Did I miss something? Hello? I got that. Whoa. This is product rule. There it is. Yes, I have that. I have that. But my notes took it further. Let's take it further. What did I miss here? Well, if I don't cancel that, and I have that, and plug my infinity in. That's infinity over infinity. Okay, I could be convinced. I didn't simplify that yet, but wait, if I'm going to take the derivative again, that is very interesting. So my notes show me that I'm taking the derivative again, and I'm a little confused because I've got this. So that's definitely infinity plus 1 or infinity. But here, 1 over infinity, that's 0. And 0 plus 1 is 1. That's infinity over 1. So, no, I don't think so. But you know, I'm going to check, because I'm a little concerned about this. So what was our original function? That was this x ln of x divided by x plus ln of x. Okay, and I want to know what happens as x heads towards infinity. Yeah, the values are getting bigger and bigger and bigger. The values are headed towards infinity. So I actually think my notes were wrong. Hold on while I cross out some stuff. Yeah, this is infinity over 1. Good. Okay, I like learning. All right, how are we doing for time? 58. All right, no more practice then, though I did want to do this one. The limit as x heads to infinity of x e to the minus x. You should end up here with 0 as your answer. All right, have a fabulous day, everyone. Take care.